In the early universe, the cosmic inflation, which is the accelerating expansions of the universe, is necessary to explain the various issues in the standard cosmology. And there are various inflation models by adopting the different potential shapes of the inflaton. And that issue satisfies the slower conditions of the scalar field to give the accelerating behavior. And usually the simple potential shape like as a power law or exponential forms are typically excluded out by the observational result like as the scalar spectral number or the ratio between the tensor to scalar. And usually the well-known modern types of the potential shapes that are given by the Starobinsky type inflation. So today we'll to talk about what is the Starobinsky inflations, how they can be arised, and what is the characteristics of this model. The Starobinsky type inflations that usually is the arise from the Earth-scale gravity as modified theories of the Einstein gravity. So the general relativity theories of Einstein can be interpreted as effective theories at the low energy. But in general, the actions can include higher order terms of the curvatures R, and this can written by the FR gravity. And the possible higher order terms are R scale or contraction between the rich tensor R mu or the Riemann tensors R mu low sigma. And especially for the early universe, the curvature scalars are very large due to the high energy scale. So the higher curvature corrections becomes very important. The equation of the motions from the polar gravities now includes higher derivatives of the matrix, and this term involves the derivatives of the FR, which introduce additional degree of freedom, sometimes called the curvature term, as the additional extra scalar mode, and this can make the auxiliary scalar field, which can be reduced by the equation of the motion. So let's consider the ballooning action. Originally, there is FR term in the Lagrangian, but we can rearrange this term with the auxiliary field chi. So that's just a rearrangement. FR is just written by the F chi here. And if we vary the actions with respect to this auxiliary field chi, then this gives the following equations of the motion. And when the second derivative of the f prime is non-zero, then this equation implies the chi should be the same with r. So if the chi should be the same with r, then the first terms are balances automatically, and the second terms reproduces the original action. So the two formulations are just equivalent, but written by the physical auxiliary field. So now we can define the scalar degree of freedom, capital pi, as the derivatives of the up. Then action can be written through in terms of the pi. Here the potentials given by the pi r minus fr. So this is just the adding the pi r term and the minus the pi r term. So this is just the equivalent formulation. And then now we will rewrite this scalar field so that the FR terms becomes just Einstein gravity, but instead of that new scalar field pi is coupled to the gravities non-minimally and non-trivially. This is the additional scalar fields pi, which becomes the dynamical, and such transformations are called um, transformations from the Jordan prime to the Einstein prime. For the specific example, we can consider that the quadratic term are scarce with the Planck mass for the dimensional analysis. The new scalar process are known as a scalaron, and this will becomes in Platon field when we list the theories regarding the Einstein prime with the canonical kinetic term. So here is the strategies how that we can transit from the Jordan prime, the FR, to the Einstein prime, just the standard GR with the only the curvature term. The scalar periods pi will couple to the gravitation non-minimally, and this form is called the Jordan prime action. And we want to realize the theories in the Einstein prime, where the gravitational factors take a standard Hilbert action. To do this, we will perform the rescaling of the matrix. This is the bar transformations or the conformal transformation. And this under this rescaling, we can compute the fundamental quantities of the GR, like the Christopher symbol, Riemann curvature tensor, Ricci tensor, and Ricci scalar. And Ricci scalar is another transform as the following form. The inverse of the pi and the logarithm of the pi. And multiplying the pi, then we can obtain the standard Hilbert action. And the additional the long variations of the logarithm of the capital pi correspond to total derivative, so this can be dropped out by the integration of the part. But the binary terms, this is not total derivatives, this is a partial one. So the last term generates the kinetic term for the capital pi, which is the non-trivial term. And similarly, the volume elements, the determinants of the matrix, also transformed with the factors of the capital pi. So combine this result, transformations of the R and the transformation of the volume elements and the rescaling, and then we can obtain the Einstein prime action. Now the Hilbert's actions are reproduced, but there will be the non-trivial kinetic terms of the scalar field. This term drops out, and sometimes cancelled out between the pi and the remaining potential term, which also comes from this transformations of the volume element. So this is just a standard reproduction for the first term, but in Einstein prime, the scalar field has a non-canonical kinetic term, and the potential shapes will be different. So to obtain the canonical scalar field, we can define the small pi as a logarithm of the ln pi, capital pi, because the denominator is with the capital pi. And this can be rewritten in terms of the capital pi. So in terms of the new scalar field, small pi, the actions can be simplified with the canonical kinetic term. Then the potential terms are now the changes. So the Einstein prime potentials includes some complicated form, and now the higher curvature theory can be written with the standard Hilbert actions with the scalar fields in terms of the canonical kinetic term. And then by using this gravity theory from FR to the Einstein prime, we can construct the Starobinsky type impulsion. Now the new scalar field pi applies as in Platon field. So let's consider that the Starobinsky potential. Already we set the FR with the quadratic term. Then the new scalar field capital pi are given by the first derivatives of the up, so in the following form. And we want to obtain the potentials of this new scalar field, and the definitions of the potentials are following: pi minus r by pi times r minus the fr. So the again, here the chi is the same to the r. The chi pi minus the f chi. And we know that the relation between the scalar field pi and the chi, the curvatures. So we can release this relation in terms of the chi. So by inserting that, we can represent the potential only in the scalar field capital pi. And we know that the relation between the small pi and the capital pi, in the Einstein prime potentials, that given by the v pi, which is determined by the u of the pi, and we know that the relation between the capital pi and the small pi. So the final results of the Starobinsky potential of the small pi are the following. And because we set the small pi as a logarithm or exponential of the capital pi, this makes the potential form includes the exponential of the minus pi over the m Planck. If we draw this potential near the large pi, this is almost a constant, and near the pi equal to the 0, it has the minimum, and that becomes a quadratic. So this can satisfy the slow roll impulsion naturally, because there are nearly constant latches when the pi values are very large, and these large values of pi correspond to the large curvatures in the early universe. So we can determine that this Starobinsky implications model from the gravity. Then we can analyze how this potential shape keeps the implications and the several behavior. So here's typo. So impulsion dynamics can be determined by the slower parameters with epsilon and eta. So by inserting that the potential shape, we can evaluate the slower parameter epsilon and eta. And the implications are only occurs when the slower parameters are both small. And for the large values of the pi, its exponential factor is small, so automatically the slow roll conditions are satisfied, and the implications that are finishes when the slow conditions is broken, which is the epsilon is equal to the 1. And also one can evaluate the number of the epochs into these implications by dividing the capital N. And by inserting the potential form, then the capital N can be determined. So, and using a relation between the slower parameters, then there will be some relation. Epsilon and n can be written by the capital N, and also for the spectral index of the scalar and the tensor to scalarity of ns and r can be written by the epsilon and eta. So the prototypical values of the epsilon 60 epoch implication, then the Starobinsky implication will give ns as 0.96 and r as 0.003 to the 0.005, which is excellently consistent with the current observation. In the remaining time, I want to talk about the mass scale of the this implication model. The overall mass scale of the Starobinsky model can be determined by the observed amplitude of the scalar perturbation. The quantum fluctuations of the Platon fields are determined by the Hubble horizon size. The delta pi is given by the Hubble over the 2 pi. And this in Platon field fluctuation translates the curvature perturbation through the relation between them. We'll cover this again in the primordial perturbation path in the cosmology series. So the curvature path spectrums PS is determined by the scarce orbit, and we know the slower conditions, so that we can replace some terms in this formula. Then the curvature path spectrums can be realized in terms of the potential or slower parameter or any board one. So the observed values of the power spectrum of the 10 to the minus 9, which comes from the anisotropies of the CMB, is around the 10 to the minus 4 to the 10 to the minus 5. And the typical values of the N is the BF to the 60 E board. So the mass scale here, which come from the parameters of the Starobinsky potential shape, so typically 10 to the 13 CV. Also, we can evaluate the leading temperatures. After the inflation stabilizes, the Starobinsky potential becomes approximately a quadratic around the minimum, so the inflaton show that the current oscillations around this minimum. And the inflatons will indicate to the standard model particle, those gravitational surplus and couples, and this make the transitions of the energy from the inflaton to the radiations, which make the heating. The decay rates can be evaluated and the leading temperatures can be evaluated, and by using the typical mass scale of the Starobinsky model, then we can evaluate the leading temperatures as order of 29 CV. The Starobinsky implications can get some variations. The boson, which is Higgs implication, and the other possible one is the alpha attractors. For the Higgs implication, now the Higgs field got the non-minimal coupled to the gravities. For example, in the second term, there's H squared and the R. Like as the Starobinsky model, we can transform this theory to the Einstein primes with the conformal transformation. Then again, the Higgs field will gives the non-minimal coupling. The alpha attracted case, the kinetic terms has some non-canonical form. For the second term, in the denominator, the kinetic term is quite complicated. And especially the denominators are balances at the pole. So to get the canonical kinetic terms, one can introduce the new scalar field, transform from the curly pi to the standard pi. And by under this transformation, typically gives the relation between the curly pi and standard pi with the tangent hypertangent, and this gives the potential shapes as the exponential form, which is the Starobinsky type model. So today we discussed the Starobinsky model of the inflations. This can arise from the higher order corrections with upper gravity. By introducing the new scalar field, we can perform the conformal transformations from the Jordan prime to the Einstein prime, and this gives the potential shapes like an exponential form, and this includes the plateau structures in the large field value. So this can naturally provide the slower inflation dynamics. We also discussed the other plateau type inflation model like the Higgs inflation and alpha attractors are the class of the Starobinsky type inflations.